Welcome. Today we are continuing with our induction proofs. We are looking at Discrete Mathematics and its Applications by Kenneth Rosen. I'm using the 7th edition. So my question comes from chapter 5.1, question 18. Yours might vary if you're using a different edition. This is asking us to prove that n factorial is less than n raised to n for all n greater than 1. So we're going to prove this by induction. On n. And as always, we're going to establish a base case first. So for n greater than 1, n is an integer, obviously, we're going to start with n equals 2 and see if the inequality holds. Now for n factorial, we have 2 factorial plus 2 times 1 is 2. We'll think of this as the left-hand side. And then for n raised to n, we have 2 raised to 2, which is 4. And that's the right-hand side. So 2 is indeed greater than 4. So the base case holds. Now, before we move on to the inductive step, we're going to be building inequalities. Assuming the minimum amount of knowledge here, we're going to start with, let me explain it this way. We're going to, let's say I have some value 1 is less than 4. It's an obvious statement. Now I can take 1 and compare it to 2 and say, well, obviously 1 is less than 2. I can also compare 2 and 3 and say 2 is less than 3. And I can compare 3 and 4. And that leads us to this chain of inequalities, which by transitivity will lead us to 1 is less than 4. The idea here is the same. I'm going to be looking at either side of an inequality and try to build so that I could stream them together and come to some conclusion. So the inductive step, we're going to assume pk, meaning the statement is true up until some integer k. And our statement here, we're going to replace with k. So it's going to be k factorial is less than k raised to k. We're going to assume this is true. And this is what we call the induction hypothesis. Or IH. So we're assuming that's true for some value of k, up till k. Now let's write down what we want to show. This is good practice. In other words, the pk plus 1 case. And we're going to replace k factorial is less than k raised to k with k plus 1. So what we want to show is k plus 1 factorial is less than k plus 1 raised to k plus 1. And we'll put a question mark over that inequality because that's what we want to show. We're not assuming that's true. We're showing that's true. So let's look at the left-hand side first. In other words, the k plus 1 factorial. Now, I'm assuming that you're somewhat familiar with factorials, but let's kind of review what they are. If I have n factorial, this means that I have n times n minus 1 times n minus 2, dot, 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 all the way down to 1. Some people omit the 1. I like it just so that we're consistent, that we're going from n all the way down positive integers. So I can group this however I want. This from n minus 1 all the way down to 1 is actually n minus 1 factorial. I can do that at any point. I could start at n minus 2 and say, well, n minus 2 factorial is that grouping. So I'm going to do the same thing for the left-hand side here by looking at what is k plus 1 factorial and group it a little differently. And the reason we want to group it a little bit differently is so we can use the induction hypothesis. So this is equal to k plus 1 times k minus 1 all the way down. And so we're going to group the first k integers and say this will be equal to k plus 1 times k factorial. All right, the reason, again, is because by the induction hypothesis, we're assuming that k factorial is less than k raised to k. This is our assumption. So I'm going to multiply both sides of this by k plus 1. Now, k itself is greater than 1. So that means k plus 1 is greater than 1. It's actually what we need is to be greater than 0, but we can see it's positive. So if I multiply both sides of this, I don't affect the inequality at all. So the left k plus 1 times k factorial is less than k plus 1 times k raised to the k. All right, so now for integers, and this should seem obvious, if k is positive, greater than 1, then k is going to be less than 1 more than it. So k is less than k plus 1 is true. Now you can check this, right? 1 is less than 2, 2 is less than 3. So what I'm going to do is I'm going to start with k is less than k plus 1. And this is true, obviously, for k greater than 1. Now k, again, is positive. I can multiply or take each side to that power. So I'm going to take each side to power of k. I'm building inequalities. So k raised to k is greater than k plus 1 raised to k. Now, k plus 1 is positive. It's greater than 0. In fact, it's greater than 1. So I can multiply both sides. By k plus 1. So what I get here is k plus 1 times k to the k is less than k plus 1 times k plus 1 raised to k. Okay, so let's look at what we have. I'm going to write down the first half here. We had k plus 1 times k factorial, which we said was the same as k plus 1 factorial, is equal to k plus 1 times k factorial. We're saying that's less than k plus 1 times k to the k. And up here, we said that is less than k plus 1 times k plus 1 to the k. Now, there's definitely quicker ways to go about these things. Again, I'm building inequalities. That's the intention, so that you can see all of these steps, but you don't have to include all of these steps as long as you make a rational argument somewhere in here. You don't have to do all these steps, but this is, I think, the easiest way to see this. Now, let's look at this. This is a raised to 1. And if I have the same base raised to the different powers, I can add those powers. So this becomes the base of k plus 1 raised to k plus 1. So notice now we have k plus 1 is equal to k plus 1 times k factorial is less than k plus 1 to k times, or k times k to the k is less than k plus 1 times k plus 1 to the k, which is the same as k plus 1 raised to k plus 1. So this means that by lovely transitivity, this is less than k plus 1 to the k plus 1. If you need a review of powers of exponents, you can look at lecture 4, I believe, or 3 in the algebra section. It goes over all of the exponent rules. So this is it. This is done. We've proven that n factorial is less than n raised to n for all values, all integers greater than 1. That's it. All right. Thank you for watching. Like and subscribe if you can. Leave a comment. Do all those things. And have a great day.